So in our last class, we have discussed about space lattice, and today's first topic is cell. So what is basically a cell? If we have three different vectors A, B, let us say we have three different vectors, vector A, vector B, and vector C. So with the help of these three vectors, if it is possible to construct a parallelepiped, then it is called or it is known as a cell. So if we draw a diagram, this is our A vector, this is B vector, or this is vector C. And the angles here BC, A is not there, so BC, we can say it is alpha. AC, B is not there, so we will call it as beta, and this one AB, C is not there, so we will identify it as gamma. So these are the three different angles between two different vectors. So now we have three different vectors, vector A, vector B, and vector C. And if it is possible to construct a parallelepiped with these three vectors, then we will call it a cell. So this is the parallelepiped. So we have constructed a parallelepiped with the help of these three vectors A, B, C, and this is called a cell. This parallelepiped is called a cell, and the angle between this B and C, where A is not present, so it is alpha. Angle between A and C is beta. Angle between A and B is gamma. And then next is primitive cell. The smallest the smallest cell with lattice points at its eight corners has effectively only one lattice point in the volume of this cell is called a primitive cell. So it is the smallest cell, and if there is uh, in this parallelepiped we have 8 different corners, 1 2 3 4 5 6 7 8. And if these 8 corners is having one atom in 8 corners, each of the 8 corners one atoms, and effectively that volume, this volume is having only one lattice point, then it is called a primitive cell. So the definition, if we go for the definition for this primitive cell, it is the cell which have atomic packing factor is equal to 1, means 8 atoms in corners, is called a primitive cell. A primitive cell. Like in this corner we have one, here we have another one, like this, and in this point we have another one, like this. In 8 corners we have 8 atoms, and in this volume, in this parallelepiped, if we calculate it, so one of the 1/8 of this atom is inside this parallelepiped. So if we consider, if we consider this one, let us say we are considering this one. So 1/8 part of this is lying into this parallelepiped. So like this, in 8 corners we are having 8 atoms, and for 8 corners will come 8, and effectively it will come only one atom into the whole volume of the cell. So this is our primitive cell. Now we shall talk about our next topic, which is Brevis Brevis space lattice. Bravais space lattice. Conventionally, the finite presentation of space lattice is done using unit cell, which show maximum possible symmetries with the smallest size. So, what is the meaning of baby space lattice? The possible maximum symmetry should be there in the smallest size. The size should be smallest, but the symmetry should be maximum in this lattice. So so we have to know about the symmetry. What is symmetry in this case? Maximum symmetry with minimum or smallest size. So in this case, we have to know about that symmetry. What are the different types of symmetries? So in the last lecture, I have discussed about rotational symmetry, translation symmetry. These all are symmetries, different types of symmetries. One is translation symmetry. I have discussed it with a suitable diagram. Then rotational symmetry. I have also discussed this topic also. And the last one is reflection. This is not in your syllabus right now. Reflection symmetry. So what are the consideration of Brevis space lattice? First of all, symmetry should be maximum and size should be minimum. These are the different consideration for Brevis space lattice. And what are the different types of symmetry? These are the different types of symmetries. So Brevis concluded that there are only 14 possible space lattices or unit cells which are having maximum symmetry within minimum size. These belong to these 14 possible space lattices belongs to 7 crystal classes. 7 crystal classes. And these are the 14 14 different these are the 14 different space lattices, Brevis space lattices, which belongs to 7 crystal classes. So what are the 7 classes? First is cubic crystal. Cubic crystal. This cubic crystal is having 3 types: simple cubic, body centered cubic, and face centered cubic. Then tetragonal crystal. Tetragonal crystal. This tetragonal crystal is having 2 different types of space lattices. One is simple tetragonal crystal and another is body centered. Body centered. Then the third one is orthorhombic crystal. Orthorhombic crystal. These are the 4 different orthorhombic crystals. 4 different orthorhombic crystals. Simple body centered, face centered, and end centered. Then fourth one is hexagonal crystal. Hexagonal crystal, only one type is there for hexagonal crystal. Then rhombohedral crystal. Rhombohedral crystal, only one type is there for rhombohedral. Then triclinic crystal. Triclinic crystal. This is the triclinic crystal. And the last one is monoclinic crystal. Monoclinic crystal. There are two types of monoclinic crystal. One is simple, another is end centered. So these are the seven classes. These are the seven classes: cubic, tetragonal, orthorhombic, hexagonal, rhombohedral, or trigonal also you can say. Then triclinic and monoclinic. And total number of space lattices are 14 as per Brevis. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. These 14 space lattices. So these are Brevis space lattices which are having maximum symmetry within minimum size. Maximum symmetry within minimum size. So these arrangement of space lattice points in the unit cell has been considered with number 1, 8 corners. 8 corners which are indicated by P. Then 8 corners and 1 body center. One body centered. Number 3, and this is indicated by I. Number 3, 8 corners and 6 face center. This is indicated by F. Fourth is 8 corner and 2 opposite faces. This is C. And the last one is hexagonal unit cell. Hexagonal unit cell, which is having 12 corners. 12 corners of the hexagonal prism and 2 center of the hexagonal faces. 2 centers of hexagonal faces. So you can find over here PIC, and F. So these are the meaning of PICF. These These are the meaning. P is a primitive cell which are having 8 atoms in 8 different corners. Here you can see in this space lattice we are having 8 number of atoms in the corners. I is body centered, 8 corners and one in body, one in the middle of the body. F is 8 corners and one in each of the faces. So here you can see in cubic, I already have told you, in cubic there are 3 types of cubic cells. One is simple. In simple, these vectors are a, b and c. A is equal to b is equal to c, and the angles between these arms are alpha, beta and gamma. So alpha is equal to beta is equal to gamma is equal to 90 degree for simple. And this is body centered. For body center also, a is equal to b is equal to c, and alpha is equal to beta is equal to gamma is equal to 90 degree. This is face center. For this one also, these arms are equal, and the angle between these two vectors are 90 degree. So like this, here a is equal to b, not is equal to c, but all the angles are equal and these are 90 degree to each other. Here also you can find a is equal to b, not is equal to c. A is equal to b, not is equal to c. Orthorhombic. In case of orthorhombic, no any arm is equal to each other. So a not is equal to b, not is equal to c, but the angles between alpha, beta and gamma are equal, and these all are 90 degree to each other. These are orthorhombic. And for monoclinic you can see a not is equal to b, not is equal to c. A and gamma, these are 90 degree, but B is not 90 degree. B can vary. So here rhombohedral, for rhombohedral, A is equal to B is equal to C. Sorry, A not is equal to B, not is equal to C. And these angles are also not equal to 90 degree. So here 14 space lattices which are called or which are known as Brevis space lattice, which are having maximum symmetry with minimum size.